So, my name is Guixing. How many of you have ever used, ArcGIS or GIS like the scenes? Good. Okay, great. So, my name is Guixing. I'm a senior research scientist working at S4, and I'm not quite sure how many of you are familiar with S4. So, the story is Brown does not have like a geography department or any like spatial science like programs here. So instead we have like a spatial science like a research institute called S4. Spatial structures in the social sciences. Okay, so basically we take care of all the like requests related to like a spatial, related to like a GIS. And we help like faculty members, from school public health, from medical science, many of them have been collaborating with us to like a grad to, especially for like for grant like preparation. Yeah, so but we also have like a GIS Institute, which is held like twice a year in summer and also in winter time, in winter like a break time. So if you want to take like a systematic like a training on GIS, on spatial science, feel free to reach out to us. So that training is about like 2 weeks. So yeah, and it's mainly designed for like a postdoc, PhD students, and also faculty members. Today, we're gonna be talking about like how to use like R to do like a spatial analysis. For some of you who are not a big fan of like ArcGIS. Yeah. Okay, I'm not a big fan of ArcGIS. So anyway, so I think we have only like 1 hour, maybe like 15 minutes. So I don't want to dive into too much like theoretical like stuff. Okay, today I'm just walk you through like a tutorial and give you some like hands-on like experience about how to use R to do spatial analysis. First of all, let's talk about like packages. I think that's kind of like a questions I got from so many of you. So many people asking me, hey, Guixing, where should I start from? Okay, I wanted to use like R to do like spatial analysis, but which packages can be useful for like spatial analysis? So if you want, R is pretty good to archive like packages and develop like documentations. So those 2 links on the screen, one is called like CRE and like a task view on spatial analysis. The second link is about like spatial temporal data and a spatial temporal like analysis. I would suggest you start from the first one, but as you might know, this page pretty long. You will still feel like lost when you first time like go visit this page. So for some of you, if you do not want to go to with the data page here, I would just give you like a short like summary for especially for people as like beginners, which packages should I start from? Okay. The first 2, if you just wanted to do, okay, I just wanted to start with like a GIS data. I just wanted to start doing like some like geometric like operations. The first 2 here, one is called SP, the other one is called SF. You should definitely start from there, especially SF. Okay, SF means like a simple feature. Okay, SP is kind of like the older version, like a spatial package, which was very popular, but now SP was being like replaced by SF. So if you haven't had any experience with R for spatial analysis, you just want to find a package to start from, go check out like SF. Okay. For raster data, you have another 2. Those two are the most like popular ones. One is called raster, the other one is called Terry. Like I said, raster is kind of like your old friend, but now raster is being replaced by Terry. Okay, so if you deal with like raster data, go with here. I'll be good to hear Terry. Okay, if you do not have any like experience with like the packages with R for spatial like scene, let's just go to like Terry. If your data is raster data, like image data. Okay. Also, if your goal is to make some like maps, you want to create like beautiful like symmetrical like maps, you want to demonstrate your work, we have like 2. I would recommend those 2 like packages. One is called T-map, T for semantic, so T-map. The other one is the ggplot2. I think many of you are familiar with like ggplot2. So yeah, T-map is kind of like customized like or spatially oriented like a graphical like a package. I'm gonna in this tutorial we're gonna be using like a T-map to do some like a plotting or mapping stuff. Okay. But if you want to produce like a high quality, like a publication quality, like map, definitely you want to go to like a Guixing project. Yeah. So also those two can like packaging for general like processing. Here, those two packages are for like map making. If your goal is about like to do some like very advanced like spatial statistical like analysis, here you can still use like SF or SP to do some like geometric like operations. So for example, you want to tell if those points are within like which polygons, SF, SP can do that. Okay. But if your goal is to do some like very advanced like spatial statistics, here are list like packages that might be useful for you for your project. So for example, if you are dealing with like arrow or lattice like data. So for example, you are dealing with like sensor track data, you are dealing with like a state like map data. You want to run some like spatial regression. Those two packages might be your best friends here. One is called spatial regression, spatial reg. The other one is called SPDEP, which stands for spatial dependence. So SPDEP will be helpful for you to construct spatial weights matrix. So for example, you want to build like a matrix where people can tell if this polygon is connecting to which polygon. So SPDEP can help you to achieve that goal. Spatial regression is used for like doing some spatial regression here. Also, if you are a person from like school public health or medical science, your research projects basically involves with a lot of like stuff about like hypothesis testing. You want to tell if a pattern is different from like a pattern generated by like a non-hypothesis. Many questions are related to that part. So if you are a person from like spatial epidemiology, school public health or medical science, those two packages might be your best friend to start from. Okay. For social sciences, where my interests are, we have also like two packages here. Like I said, it's kind of like some popular like packages. So one called SEG which stands for segregation. Also OSSR. OSSR is kind of like a comprehensive like a segregation like a package. Okay. Or if you are from like political science or crime like an analyst, your goal is to analyze a bunch of like discrete like points in the space. For example, I have a data set which has all the locations about like crime incidents in Providence. You want to do some like spatial analysis over there. You want to see if this pattern is different from another type like a pattern. So that kind of analysis in GIS world or in spatial world is called point pattern analysis. And SPAT, STAT, that's the best package if your research project involves with like point pattern analysis. Geostatistics is mainly for environmental science guys. So their goal is to do like interpolation. So for example, if your goal or research is about to generate like a continuous like surface of like temperature or elevation, and geostatistics is a tool. Okay, and here there are two packages here. One is called DSCoV, the other one is called GUR. So here is kind of like short overview of spatial packages. If you do not want to go to they're like comprehensive like a list, you can just look at those packages to do some like exploration analysis here from there. Questions? Sure. Why spatial is different? Why do we have to go to like spatial packages rather than sitting with like a normal like packages? So for spatial data, the biggest or the distinctive feature is the data has coordinates. We do not deal with like data like row by row.
I should be used on.
I'm sorry.
I should be used on.
Oh, okay. Yeah. I used to offer like Python training. So yeah, in PIPC. So if your goal is to do like spatial automation, for example, your project involves like a massive data set. You have like 1,000 like data sets. and your goal is to automate your spatial analysis like workflow. If that is the case, definitely Python is the best friend rather than R. Why use R? Okay, statistics. If like I said, I mean, if you look at R or spatial, you rarely see those words in Python world. Those tools are mainly designed by statistical people. And if we just talk about the difference in terms of like spatial analysis between R and Python, I would say Python is way behind. Because Python is more about like automation, it's more about like computer science. It's more about like a geometric operations. For example, I want to tell each this polygon is overlapping with this polygon, something like that. Definitely you can use R to achieve that. But if you are talking about like spatial statistics, especially hypothesis testing, I'm sorry, Python or those like Python packages in spatial is not your friend. Yeah, so.
Is there any difference in performance? Python?
Definitely Python should be faster, but here it's really a question depending on how large, how big your data is. I don't want to do that one. Yeah, so. But definitely R has some like parallel like computation like packages, which you can use to speed up your analysis. But that's not a story. Yeah. So. Will we continue? Yeah. Now let's look at the data structures and formats. So in GIS or in spatial world, we have two types of like data sets. One is called vector data. The other one is called raster data. Vector data, basically all the like objects in the real world are represented by points, lines, and polygons. Okay, so when we talk about a GIS or spatial analysis, how one geometry is related to the other geometries is our kind of like interest. So if you deal with the vector data, your data set are points, lines, and a polygon. And also points have some like attached like attribute over there. Raster data is mainly used for modeling. Yeah, I'm gonna answer the question later. Raster data is mainly used for modeling or representing some like continuously like very like a phenomenon. For example, temperature. For example, like elevation. For example, you can just think of raster data as like an image. When you use your phone to take like a picture, the picture is a raster data set. Yes. Questions?
Yeah. So is it just X, Y,
You have you have coordinates, but also you have like other non-spatial attributes. Yeah.
Oh, yeah, but is the spatial data is 2D?
Can be 3D, can be 2D. We're gonna touch up on that part. Pretty soon. Okay, now let's look at data. Like I said, this is kind of like training. We have only like 1 hour, so I don't want to dive into the theoretical stuff. If you want to get like systematic like a knowledge about the GIS or like spatial analysis, highly recommend that you check out our website or reach out to us. Okay. Let's look at the data or file like formats. Here, if your data is vector data set, highly likely you will run into one file type for like shapefile. How many of you are familiar with like shapefile or have ever like download data? Okay, good. So shapefile, one big like misunderstanding from the public is shapefile is a file or is one single file, but it's not. Shapefile, when you go to some like website, for example, like a Census Bureau like website, you want to download like a sensor track like a polygon data from Census Bureau, highly likely you will get like a zip file, a compressed file. If you unzip that file, you will see a bunch of like files coming out of that zip like file. Okay, they all share the same common name. If we now look at the file extensions, So this is kind of like a shape file, like a format. Okay, it has a bunch of files that share the same name, and each of them has a different part of information. Okay, if you want to use like shape file, you have to read or use all of them in your JS program or in the package. Okay, I'm going to tell you what kind of information each of them have. So let's start from the DBF here. The file extension. Okay, DBF has information about all the attributes or like non-spatial information. Let's say you have like a bunch of like points. Each point should have its own like non-spatial attribute. For example, if let's say each point is a sensor track like a centroid. Okay, maybe you have like some like household income like information over there. Those things will be organized in this like DBF file. Okay, PRG file here. PRG file has all the information about like coordinate reference system. So just as the question from the attendant, is vector data is 2D or 3D? It depends. How could I know? PRG file has that information in there. PRG file will tell you what kind of like a projection, projection information this data has. So if you just want to tell if this data is 2D or 3D, go to PRG file. But for many like JS people or for like data analysts, you don't have to go to each of them. After you add the data into like JS program, you can read all the information from the UI. So that SHP has all the geometry information, like coordinate. Okay, so basically shapefile organize spatial information, non-spatial information in different like files. Okay, SH is just a spatial index like information that will help you or help like a JS program to speed up like analysis. So PRG file is one of the most important ones. .hp has the geometry, has all the coordinates information. DBF has all the non-spatial information, which are organized into a table. Okay, we're gonna see the data, shortly. Here, just give you like an overview what you are dealing with. GeoJSON is another popular like vector like format. If you do a lot of like web mapping, or if you go to some like open data portal, if you like click like download data, you will see that option. So if you want to download your data into like shapefile, or if you want to download your data into a GeoJSON. GeoJSON is kind of like an extension of JSON format. So in there, you can see the information are organized into like a key value pair. Okay. Yeah, now let's okay, I'm not like a raster like a data like a expert. So I don't want to talk about too much about like raster data. If you have questions, I think environmental science like program or department might be your friend. Okay, not me. So here I'm gonna walk you through like a tutorial or a lab to help you to gain some like hands-on experience. So in this lab, we're going to do something to explore the relationship between obesity and outdoor recreation facility at the town level or sub-county level. Okay. Now it's the time to get your hands dirty. So I want you, first of all, I want you to go to click, those two links to download data. Just either one. Yeah, I put data, into like two like website, just in case, one of them might fail. So you can just choose, click on either one. You will get a zip file, and please put your file. Maybe I can do some demonstration. Okay, so in my case, I'm gonna create like a folder on my desktop called R4 Spatial, and I'm gonna like put the data into that folder. Now you can unzip that file. Okay. So here, how many of you have downloaded the data to your computer? Good, good. Okay. So we have three data sets here. Two of them are GeoJSON. Okay. If we open them in the GeoJSON file, it's just like a text file. Yeah, it's just a human readable like text file, but you don't have to look at them. Another one is a shapefile. Okay, shapefile is not a single file. This is kind of like a question I got, trouble I got so many times. When I ask people to share with me their data, they just gave me like one of them. If you want to share like JS like shapefile data, you have to share or dip all of them into zip file and pass it along to your colleague. Okay, because shapefile organize information into different files. Okay, each of them are very important if you want your colleagues to open that file. Okay. Now let's open RStudio. Let's create like a new R project. Okay. Let's create a new project. And choose like exiting like a directory. And navigate it to your data folder. So in my case, my data is downloaded into a folder on my desktop. Okay, called R4 Spatial. So I'm gonna create like our project in data, living in data folder. And I create a project. So basically, what I did just now is I created like our project. In the same like data folder, in the same like data folder. Okay. Now let's add like a new R file or R script file. Go to file and go to new file and choose R script. Before we start typing the code, let's save this file. Okay, just give it a name. Like whatever. Okay. Now, in this tutorial, we will be using three packages. One is called SF, which we will be using to deal with spatial data. The other one is TMap. We will be using TMap to do some like plotting, to do some like map making, to make some maps. And also we will be using a TDverse to do some like a general like a non-spatial like a table like processing. Okay. So if you do not have those packages, you can I'm gonna give me 1 second. Yep. So we will be using like 3 packages in the tutorial. One is for SF. The other one is for the TD-verse. The other one, the third one is KMap. Okay. And you can go to like a menu, go to tools, and go to install packages. So you can type like TD-verse to download that package. Okay, do not try to install the packages from the source. Okay, that will be taking so long. Just let me install them in the binary like version, especially for like a Mac people or app. Okay, or Ubuntu for people who are using like a Ubuntu. Just let me install the packages coming from the binary. On the binary version. Not try to like compile like a packages. You can do that later on, but that will take like much longer. Yeah. Those 3 packages, one is SF, the second one is TMAP, the third one is TD-verse. Okay. I'll give you like 2 minutes to install those 3 packages. Yeah. Yeah, do not install packages from the source. Okay, especially for now. Yeah, just click no. Yeah. But that will take longer. How many of you have installed those 3 packages? Okay, great. So let's continue. Okay, so we just download 3 data sets. Okay, I want to give you like short tour about what those three data sets are. The first one is a point location data, and each point depicting showing you the location of some recreation facility, which can be a ball field, which can be a playground, which can be a basketball or tennis court. Okay, if you make a map from the data, this is kind of stuff you will see here. Each point has their location. Each point has some a non-spatial attributes attached to each point here. Okay, and the data is downloaded from Rhode Island GIS platform. The second data is called sub-county or GIS sub-county Rhode Island Rhode Island town boundary data. Okay, the data is downloaded from Census Bureau. So for many of you, if you do not know where to start from, if your goal is to find some boundary data, Census Bureau is your best friend, has the best data. Okay, so if you visualize the data, this is kind of the polygon data. This is not a point data. This is kind of polygon data, and each polygon has the boundary. Each polygon shows the boundary of a town in Rhode Island. Okay. The last piece of a data set is about Rhode Island census tract obesity rate data. That's a data set have been downloaded from CDC. Okay, so each point here, each point is also a point data, as you can tell. Each point represents the centroid of census tract. So census tract is supposed to be a polygon, but here the data is a point data. So each point here represents the centroid of a polygon. And also each point has the information about obesity rates. So here, this tutorial will be walking you through analysis where we can investigate the relationship between the obesity rate and the recreation facility rates. Okay, which is a very simple test. But the goal is to help you to understand how to read spatial data how to like run like a spatial analysis with R. Now let's start like coding. So let's load the packages, those 3 packages first of all. So library function is a function with which you can load the packages into your environment, R environment or session environment, whatever you name it. Okay. And the first step, we should, like I said, load like packages. And then we want to load like data into this R session. Okay. So we have 3 data sets. So let's read the town polygon data first. Okay, let's call it towns. And then we're gonna use this function to read a data set or spatial data set into R. That is st_read. Now when you need to pass in like a file path. Okay. So if your data is located in the same like folder, this project, like our project folder, this is what you can do. So if you go to here, this panel, click like file, where you can see the data folder. Okay. Click on data. And let's copy like a folder path to clipboard. This is just one way to figure out how to get the file path.
You want that one to be read SF?
I'm sorry.
You want that one to be read SF?
Oh, I'm gonna show you different ways to read. Like there are 2 functions actually. This is the one function with which you can read like spatial data. There's also another one. I want to tell you the difference here. So we have 3 data sets. The other one is obesity. Another way to load your data into like this R session is instead of using like absolute like a file path here, which is very, very long. Another way is to use like a relative like a file path. So for example, you can just start with like a dot and backslash or slash, and click on like a tab on your keyboard. You can choose data. If your data folder is sitting in the same like a folder with the R session, with this like R project. Okay. So here I use like 2 functions actually. One is called like st_read. The other one is called read_sf. So the difference between those 2 functions, first of all, you can use either one to read your spatial data into this R session. Okay. The difference between these two it is st_read is gonna produce a data frame. is read your data and turn it into like a data frame. Okay. Read SF is gonna turn your data into a table, which is the strict version of data frame. I'm gonna show you like more examples from there. But if you just want to find like functions to read like spatial data into R, you can use either one of them. But I would suggest you to read like SF, to use them in this one, read underscore SF. Because if you are familiar with like PDVerse, you know, if we want to read like CSV file, we use read underscore CSV. So here, if you want to read like spatial data, it's pretty convenient. Just read underscore SF. SF means simple features. Okay. Now, oh, I'm sorry. Now let's look at them in their class. Their classes. What kind of like an object they are? What kind of like classes they are? So you can use class function. So class, I mean, counts that variable. Look at here. First of all, it's an SF picture because that's a function from like an SF like a package. So it's like a simple feature like class. Also, it's like a data frame. So non-spatial data is read as like a data frame, basically a spreadsheet or a table. So basically data is also spatial data, but I use the read underscore SF. That one is gonna produce like an object with SF class, because first of all, it's like a simple feature like class. And also all those like non-spatial information will be interpreted or will be transformed into like a table, which is a strict version of a data frame. Okay. Now, after the data or spatial data is read into this R session, the first thing you should do is you want to know whether your data is 2D data or 3D data, or in GS or in spatial world we call it, whether your data is a project or not, or what kind of like a projection, I mean, my file is using, because you don't want to mess up with the data in the projection. Let's give you that situation. One data is talking about like latitude, longitude, coordinates. And the second data you are dealing with is project data, which means those coordinates are not latitude, longitude, they are X and Y, okay? And their unit is like a kilometer. And here, when you talk about latitude, longitude, the unit of your data is what? It's bigger. So if you want to do some like a calculation of a distance using those two data, without knowing their coordinate like system, you are messing up with their coordinate. Okay, so prior to like the SF package version 1.0, SF package cannot, well, just assume your data has like planar coordinates. Okay, they will just do like assume your coordinate system is like a Cartesian coordinate system. Okay, which will have a huge like consequences there. So I would say after your data is read into our session, you need to check whether your data is a project or not, or what kind of like a spatial coordinate system your data is using. So how can we know that? So the function you will be using is it's called ST underscore CRS. CRS stands for coordinate reference system. Okay. So if you look at it, if you run that code, that line of code, look at it here. Look at it in the console. So you will see, okay, my data. First of all, look at it here. GeoGCRS. GeoGCRS means geographic coordinate reference system. That means your data is talking about latitude, longitude. Okay, here, GUGCIS. Yeah, it has so many like tests here, but I want to draw orientation over here, GUGCIS. Okay, that's a sign of my data is talking about like latitude, longitude. And also look at me the last line of the output in your console. It says ID EPSG 4269. Okay, pay attention to the 4269. We're gonna revisit this one. EPSG is a projection authority organization. Okay. Now let's look at the CRS of the other two files. Let's look at the obesity. What kind of like coordinate system in my obesity data is using. Let's look at the last line of the output. This one is using the same like authority, projection authority, but the ID is different. This one is 4326. The last one, the first one we talked about is 4269. What that means? That means those two data sets are using different coordinate like system. And for example, we have a location here, this building, building. If your data is described by different coordinate reference system, in the data, the location of this building is different. That's why you should be aware of like coordinate reference system. Always check the coordinate reference system. Okay. So the output from that function is pretty long, and for many of you probably I don't want to read it. I don't know. How to interpret those like text. Is there any like a simple like function which I can use to tell me whether my data is projected or not? I just want to know whether my data is talking about like 2D information or 3D information. Okay, so that function is called ST is long line. So that's a simple function. That's a question telling you if your data is projected or not, or if my data is talking about latitude, longitude, or talking about like kilometers, X and Y. Okay. So if you run those three lines, you can tell, okay, they are all returned like with a true. That means your data is described by latitude and longitude coordinates rather than like a kilometer or X and Y. Or related to back into that question, your data is talking about like 3D information. Because latitude, longitude are lines on the globe. Okay. Time goes so fast. I don't think I'm gonna like finish all the things here. But the tutorial is on the website, so you can always like revisit that website. Okay. Now, next thing we should do. Let's see. Array data for the system. Oh yeah. Since data are not like a project. So let's just turn my data into like a project, like a coordinates. We want to talk about like a latitude. We don't want to deal with like latitude, longitude, because if your data is using like latitude, longitude, R or SF package is gonna use underlying package which is called S2 to do calculations on below. Basically, when you do a calculation between like 2 points, SF is gonna do like a 3D calculation. It's gonna be taking like longer. So, but if you transform your data into a 2D data using projection, okay, the calculation will be much like simple, okay, and also faster. So let's do like projection. So we're gonna be using ST transform. Okay. So here, what we are doing here is we wanted to turn or transform like latitude, longitude coordinates into X and Y, which has a unit of kilometers or meters. Okay. This function requires like two things. This function requires like two parameters. One is a simple feature object, which is talking about latitude, longitude. The second parameter is for the CRS. The other one is a destination projection ID you want to use for the projected like data, okay, which will be two-dimensional like data. So you might be wondering, okay, what is the projection ID I will be using? I mean, come to like, good to talk to like a DS like specialist. So that they will give you like the best like answer. So yeah, we will do the same thing for the rest of the two data sets. After the projection, you might need to check if your data is lie long or not. So we will be using that function again to check if my data is still talking about like a lie long or X and Y. Okay. So now it gives you like false. Your console. And it means okay, my data is projected. Now I can do some like simple like calculation. So for like a distance, for some like a topology like analysis there. Okay. Oh, shoot. Yeah, we should check. Now let's check what kind of like a projection or CRS information is now for my project like data. If you look at this output in the console, the text or output is much more. Okay, because when we talk about projection, you have to make sure you have two pieces of information. One is GCS, the other one is PCS. GCS means geographical coordinate system. PCS is a projected coordinate system. So you have two parts of information right now in here. So you just need to look at it here. Did you remember the first time we read this text? It said GUGCRS. GUGCRS means your data is talking about lie long. Now this keyword becomes PROGCRS, which means my data is projected. My data is talking about X and Y, and my data is having the unit like kilometers or meter. Here we are using feet. Okay. Maybe let's just finish the first part of the tutorial. Oh, let's make a map. Okay. Let's make a map. So you might be tempted to use like a plot that function to make a map here. So let's see what's gonna happen. Okay, because plot is kind of like a generic function. So you can just be passing any like data into that function. Plot is gonna find the red version of like a method to make a map or to make like a graphic. look at the output here in this panel. So what happened here? So that function just let me read the table and try to make like a semantic map on each of the column in my data. This is not what I want. I just want to like have like a picture of the polygon. Okay. So what are you gonna do? So this is what you're gonna do. Counts the PRG, the geometry. So here I'm still using that plot function, but here I don't want to map out. I don't want to use all the columns or all the variables in my table. Just want to just plot out the geometry. Give me the polygon map. Okay, you have to use like a $sign to refer to the geometry column in the data. Okay. Now we just made the first map of the polygon data. The polygon boundaries. So that is the town map or the town polygon map of the road island. Okay. What if I wanted to see, I wanted to produce like a semantic map using like just the one variable in my data? I should show you the data here. So this is how your data, how that file is read in our session. This is the count file. It's still like a table, but if you scroll to the right, you will see we have like a spatial column for like geometry. That's how SF package is used. How SF package or other like spatial packages can deal with like spatial data. So those like spatial packages is gonna look at it in that column and start like plotting or start like doing some calculation from there by using the coordinates. I think we should finish. The training. Let's use the T-map, which is like a map visualization like a package. Okay, I'm gonna show you how to do that. I think after that it will be okay. So let's see. Let's see, ours is not very cool because when we use like JS program, you can just do some an interaction stuff. Like I want to click on this polygon. I want to see what kind of information is there. So how can we turn R into like a JS like a program? That's the thing like many people want to see. So for that case, we're going to be using like a T-map like a package. Okay. So now T-map underscore mode. And let's pass in like a view. View is gonna turn T-map like a visualization, like a functionality into an interactive like mode. Okay. So what I just did here is I'm using some like a function from T-map that package. Okay. The first line here, T-map underscore mode view turns my R session into an interactive like a yes like a mode. Okay. And this is how you read a data or a variable into like a T-map like functions. You use like a TM underscore shape and pass in the variables or object, whatever you name it. So here I wanted to make a map on using like a tons.prg file. Okay. If you are familiar with like ggplot2, this is kind of like a syntax. Following the pattern from like ggplot2. Okay, you add like a plus sign there, hit enter, go to next line. You start writing, okay, TM underscore polygons. Okay. So here I just want to show the boundary of my town polygon map. And then you keep going. Okay, I want to bring in like another layer. I want to bring in like another like data set into this kind of like the visualization scene. Okay, TM_shape. Now I want to add my recreation layer onto that map. Okay. Now you need to add a like plus, hit enter, next line, and a tail like a T map. Okay, just to show the dots, just to show the location of my points. Okay, so TM_dots. So that will produce a map over there. Like I said, now we are asking T-map to do like an interactive like mapping stuff. Okay, so if you zoom in or zoom out that panel, you can see it's like playing with like a GS like a program. Okay, if you click on like a zoom, you will be redirected into like independent like a panel where you can click on a polygon where you can see those like underlying like attributes associated with them in that polygon. Okay, like I said, it's pretty much like playing with like a GS system right now. So you can also change the base map. Click on that thing on the left. You can change the base map of your graphic, or you can turn off or turn back on the layers you are visualizing here. Yeah. Oh, yeah, that's what did that happen? It is town. It is town. It is town. Yes. I can show you. Give me 1 second. People are living there. It's a real town. Give me 1 second. I'm gonna show you the text, okay? Then you can see. So which one? You were talking about this one here? I should move up a little bit. This one or this one? Or this one? Oh, this is kind of like, you see, if you read the text in the data, you will see it said county subdivisions not defined. So basically it's just kind of like a polygon like made by like a simple bureau. Yeah. Yeah, that's a border area. So if you go to my tutorial, you will see. Later on, I'm gonna take out that polygon out because there's no people living there. That's not like it doesn't like contribute anything to our analysis. Yeah. So the track like polygon are more like administrative like a purposes for counting people. Sometimes they will add some like an empty or black like a polygon there. Yeah. So it's common.
Okay.
And also depending on what scale you are looking at. If you go deeper, like this is a track or the track block, you might see something like that. Or yeah. So.
And so you do.
Yeah. So if you go back to my tutorial. The last step. You will see I said here. So let's remove that count and also one empty count there. Okay, because they don't have any information and they just have like any value over. Okay, it's more of like a simple slide like question. I think we're gonna stop here, and unfortunately we have only 1 hour and we didn't finish orbit. We're just gonna start. So but you can just go back and revisit my website and simply follow through the steps. And if you have any questions, you can always send my email. In the next in the upcoming like. But yeah, but let me close the Zoom. I'm gonna answer like some questions.